instead of doing calorimetry as an experiment, which is what we were going to do today, but we'll do tomorrow, instead of like physically measuring the amount of energy being exchanged, and whether it's exothermic or endothermic, we can just do it simply with a calculation. And that's where we get Hess's law. And so what they do is they look at all the individual enthalpy changes of each individual reaction, and you get a net reaction. Okay? So reactants can do the reaction in a bunch of different ways. You can have lots of your silver nitrate and only a little bit of your sodium chloride, or you can have lots of silver chloride and only sodium chloride, and a little bit of silver nitrate, or you can have equal both. You have different pathways to get to the same end products. And so it's very step by step. First, you have to figure out what the net reaction is. And then you have to manipulate the intermediate reaction. So it's going to tell us a reaction, and generally it's going to give us the end, like the ultimate reaction, and we have to figure out all of the pieces in between. And it's those pieces in between where we get the overall change in energy, or the enthalpy change. Okay? And so what I can tell you is that signs are going to become critical. So if you start out with a positive enthalpy and we flip the reaction, make sure you flip the enthalpy. You'll see what I'm talking about. And then it's just doing the net process. And it says we usually use Hess's law when the list of intermediate reactions are listed and you're trying to find the enthalpy change for the desired net reaction. So this is the example. One of the methods that the steel industry uses to obtain metallic iron is to react iron 3 oxide with carbon monoxide, as shown in the balanced equation below. Determine the enthalpy change of this reaction given the following equations and their enthalpy changes. So here's two intermediate reactions. Carbon monoxide plus half of an oxygen gives me carbon dioxide, and 4 iron plus 3 oxygen will give me 2 iron 3 oxides. And this is the amount of energy. If we ran the reaction forward, we did carbon monoxide plus half of an oxygen, we would release 283.0 kilojoules. And if we reacted 4 iron with 3 oxygens, we would release 1,648 kilojoules of energy. Okay? But what we need to do is we need these pieces here all to be in the right spot. So if I look at this example here, here's carbon monoxide, here's a half oxygen, here's carbon dioxide. When I look at this equation, where do I find carbon monoxide? On the reactants or the products? On the reactant side. So I want to write this formula. So you can see right now, I have carbon monoxide set up in the reactant spot, and I have carbon dioxide set up in the product spot. So that takes care of those two pieces. Now I look at this 4 iron and this 3 oxygen, and I get 2 iron 3 oxides. Well, where do I find those components in this reaction? Where do I find iron? On the product side or the reactant side? On the product side. I have to reverse this equation. Okay? Now I need to look. I need how many COs and how many CO2s? 3. So I need to multiply this entire piece by 3. I need how many iron 3 oxides and how many irons? 1 and 2, but I've got 2 and 4, so what do I have to do? What I do to the equation, I have to do that to the enthalpy. Because I left this equation going forwards, I've got negative 283.0, but I have to multiply it by 3. Then this delta H, what did I do to this reaction? I flipped it, so I have to flip the sign. And then what else did we do to it? We divide it by 2. So we flipped the sign, and we multiplied it what we multiplied by, or divided by what we divided our equation by. Okay? So let's write this out. I'm going to have 3 COs plus what am I going to have for oxygen? 3 halves. And then CO2. Sorry. CO2s, what am I going to have? 3. Right? We're just factoring out. And then my delta H becomes what? Your calculator's in my school bag. What's 3 times negative 283.0? This second sentence, what's 2 divided by 2? 1. So I'm just going to have Fe2O3. What's 3 divided by 2? 3 divided by 2? What's 4 divided by 2? And what's 1648.4 divided by 2? But we got to remember it's positive. Now we're going to do that whole canceling piece. So I have 3 COs on my reactant side. Do I have any COs on my product side? Okay. I have 3 halves here on my 3 half oxygen on my reactant side. Do I have any oxygen on my product side? How many? 3 halves, so I can actually cross off this whole entire piece. I have 1 Fe2. I have 1 Fe2O3 on the reactant side. Do I have any on the product side? No, so I'm going to keep that. Now let's look at my products. I have 3 CO2s on my product side. Do I have any on my reactant side? So I'm going to keep those. And I have 2 irons on my product side. Do I have any on my reactant side? So I'm going to keep those. And then my delta H is going to be the sum between these two. Negative 849 plus positive 824.2. And what do I get for delta H? So that's the enthalpy change of this reaction. Because we took 2 intermediary reactions, created our net reaction, and we found our net enthalpy change. Okay? Yes, sir. Okay, we can draw a potential energy diagram for this, remembering that these are the reactants, these are the products, and this enthalpy says what kind of reaction? Exothermic. So if I was to look at a potential energy diagram, we're going to put energy potential on the y-axis. We're going to put our reactions on the x-axis. And is exothermic a step up or a step down? Step down, which means that I can put 3 COs plus Fe2O3 here, and I can put 3 CO2s and 2 Fe's here because these are reactants and these are the products. And this change between the two is negative 24.8. This looks a little different than what's in the notes because I just did it of this reaction here. The notes looks like this. They took this intermediary right here, whoops, COs, whoops, 3 halves, sorry. And then they have this reaction here. So that gave me 3 CO2s. And my overall result. And then in here we have a secondary reaction with the Fe and the 3 halves oxygen, this part here, because this is also a product, right? And so, but this is the overall one here. I would pay attention to this one here. Okay? Number 2. Where's my number 2? Okay, let's look at another one. It says, from the following information, calculate the enthalpy of formation of solid phosphorus pentachloride. So in my mind, and this is what I typically do, where's all my pencils? This is what I typically do. It's a formation of phosphorus pentachloride. So I want I want this as a product, right? Because that's what the statement phosphorus pentachloride means. So I'm obviously going to react phosphorus and chlorine gas to get that. That's what I do when I'm trying to break down these questions of what does it look like. I know that this is what I want as a product. Riley, can you turn off the two backlights, please? They're just by the windows. One more. Keep going, down by the window. Okay? So I know that I need this one here to go in the forward reaction because this is the product that I want. And now I need it such that I don't have to deal with this phosphorus trichloride. What? Well, no, I don't. This is not a formation reaction because this is phosphorus trichloride. Yes. Okay. So how do I get rid of this? I also write this reaction going forward so that I have, because this is a reactant, I need something that has this as a product, which happens to be this equation. Okay. So now I've got to look. I have 4 PCl3s here, and I only have 1 PCl3 here. So what do I need to do so that I can cancel them out? What minus 4 will give me 0? 4. So I have to multiply all of this out by 4. And notice I put the brackets after my energy. Would I do anything to the bottom row? Nope, because I just need to get rid of this PCl3. What? Yes. So now what I need to do is I need to look at this and I need to look at my net. So if I have 4 PCl3s here and I have 4 PCl3s on the opposite side, I can cancel those out. And so I'm left with P4, I'm left with this. So I've got P4 solid plus how many chlorine gas molecules? 10. With a delta H that equals what? right? Because I add negative 500 plus negative 1272. And then we can always double check our balanced reaction. If I have 4 phosphorus here, here I have 4, that means that I have 20 chlorine, so over here I need to have 20 chlorines. So I know whether I've done my math right on my enthalpy is one thing, but I know that I set that equation up properly because I have a balanced net reaction. If you don't have a balance here in this row, if you don't have a balanced net reaction, you've set something up incorrectly, or you've canceled out incorrectly, or you've made an error. How much you have to multiply? Because I had 4 PCl3s here, and I don't need PCl3, right? I know a formation reaction is an element plus an element gives me a compound, right? That's Chem 20. So here's one element, here's my second element. This is my compound, which means that PCl3 doesn't belong as part of my reaction. So I know that I need to cancel it out. This one had 4 in it, so I had to make sure that this one had 4 in it. So I had to multiply everything by 4. Okay? Yes, no? Okay, let's look at a potential energy diagram. Okay, my first part of the reaction is I took this part here, right? This is my first reaction. P4 plus 6 Cl2s. And I got a reaction that said 4 PCl3s. And then I had 4 PCl3s reacted with 4 chlorines right here with 4 chlorines. And that gave me another reaction down here of 4 PCl5s. So this first reaction, P4s plus 6 Cl2s, this is a delta H of negative 1272 kilojoules. And then this reaction here of 4 PCl3s and 4 Cl2s, this is a delta H of negative 500 kilojoules. And this overall reaction here, yep, should be a delta H of negative 1772 kilojoules. Is there a specific that you have to make first? Just looking at this reaction, I went this reaction first, 4 PCl3s, or no, it doesn't matter. However, if you flip them, you would have it would just look like this. You would have this one. Actually, yeah, it does matter because you've got to get your 4 PCl3s created first before you could do this reaction down here. How did you get 4 PCl5? I only got 4 Cl. Here I had to multiply it by 4. Yeah. So that's 4. It doesn't cancel out anywhere along the way. There is no other PCl5. What do you need, Declan? The which? This one here? Here? This is just what I wrote. That's why I wrote it in pencil, because no, it's just photocopied wrong. It's just photocopied maybe wrong. You okay, Declan? So when you go here, Eric asked the question, does it matter which order you write it in? Yes, because we're getting rid of the PCl3s, we have to do the reaction that gives us the PCl3s first before we can do the next reaction to get us the PCl5s. Okay? Yep, yep. Okay, let's look at the practice problems. Right, that's next on the list. No, example 3. My notes printed off completely out of order. Okay, let's look at this one. Several reactions are listed below. Ethane and hydrogen give us, no, ethine and hydrogen give us ethene. Water gives us hydrogen and oxygen, and ethene and oxygen give us carbon dioxide and water. So it's a combustion reaction. It says, use the following information above to calculate the standard enthalpy change for the following reaction. 4 carbon dioxide and 2 water will give me 2 ethenes and 5 oxygens. Let's just stop and look at this reaction. Is this a forward reaction or a reverse reaction? A reverse reaction of what? Of combustion. So if it's a reverse reaction of combustion, what should my delta H be? Positive. You're right, Nolan. Or it should be minimal, because a combustion reaction is exothermic. You burn something, you're releasing energy. But to go backwards requires energy. There's a reason why that reaction happens in the forward and not the reverse. So potentially we're looking at a positive delta H. That's just something that I'm going to look for when I start doing this question. So now here we go. Let's just start. When you have questions like this and you're like, I don't know where to start, there's 3 equations. What I typically do is I find something that one of these equations offers that none of the other ones do. So here's ethine and here's ethene. Here's ethene. So I wouldn't start with those 2 because they both have ethene in them. However, one has carbon dioxide and none of the other ones have carbon dioxide in them. So I would start with this one. That's just how I problem solve. Every year students ask me, well, which one would you pick, Mrs. Pyre? This is how I would problem solve that. So I need CO2 to be where? In the products or the reactants? So I got to reverse it. Whoops. Okay, notice I circled the plus sign because I had to reverse it. All right, then from there, here's ethene. And we need to get ethine. So here's something else. Ethine isn't in any other reaction other than this one. So let's flip this one. Okay? So that's positive because I flipped it. I flipped this one and I flipped this one. So I have to reverse the sign. Now when I look at this reaction here, it says that I need 2 ethynes. So what am I going to do to this question here? Multiply it by 2. Sometimes this literally ends up being trial and error. It's just a puzzle that you have to fix. I am, because I don't want hydrogen, right? So where is my hydrogen now? In this part, in the product. So I need this one here to be reversed because I need it on this side so I can cancel it out. But the H2 is on the product side here so that I could get the ethine. No, it's not. It's on the product side here. Oh, did I miss writing something? Oh yeah, no, I flipped it. So now I need to flip this one to cancel it over here. Okay. So I flipped this one, so this is going to be negative 71.2 kilojoules. Now, we need to stop because here we actually have how many hydrogens? 4. So I need to multiply this by 2 because I only have 2 hydrogens here and I got to get rid of them completely because there's none in the balanced equation. Here I have 4 hydrogens, but in this reaction here I only have 2. I need to bring it up to 4. No, I have 4 moles of hydrogen right here. 2 times the 2 moles. So here, there's only 2. So now I need to multiply it by 2. Yeah, I said 4 hydrogens, but it's 4 hydrogen molecules. Okay? Do we understand that piece, Declan? Okay. So now, if I write this out, I don't know where it is. Okay, so now I've written out my everything. This is my total reaction. So if I look, I have 4 CO2s on the product side. I have none on the reactant side. I have 6 waters here, and I have 4 waters here. So I'm going to cross off these 4, Subtract 4 from 6 is going to leave me 2. I have 2 ethenes, and here I have 2 ethenes, so I'm going to cross those off. I have 4 hydrogens here, 4 hydrogens here. I have 2 oxygens here and 7 here. It'll come back in. I have 2 oxygens here, and I have 7 here. So I'm going to use all of these, and I'm going to be left with 5 oxygens there. So I should have this, this, that, and that. And what do I get for a sum here? Okay, so it's the same concept as net ionic reactions, net ionic equations. But now we're just trying to figure out our delta H.